The Earth's atmosphere is the last section of this chapter, and we need to think a little bit about how gases are behaving out there. There are different levels of the atmosphere. They have names, and at different altitudes we have different levels of pressure. So if you've been in an airplane, you know the pressure gets really low the higher you are higher you are from the Earth's surface. So the pressure at ground level is down here near 760, right? But as you go up in the airplane, the pressure gets reduced, and they have pressurized cabins in airplanes for that reason. So the pressure gets very low the higher you go up. The pressure decreases as altitude increases. On the right, we have the different levels described, and we often ignore these things. We hear about them. We think about the stratosphere as being way out there. Well, it's out there beyond the troposphere. The troposphere is where things grow, the growing region, and the stratosphere is beyond it. And so the altitude is in kilometers here. And so if we're thinking in terms of 20 kilometers, where do the jets fly and where are the temperatures higher and lower? Well, let's think about it. At the Earth's surface in the troposphere, what are the temperatures going to be? Well, probably somewhere in these ranges between the freezing and boiling points of water, kind of. And sometimes they're below, sometimes they're above. Depends on the weather and the season. The stratosphere, as the higher up you get, the colder it's going to be. But once you get into the stratosphere, it warms up again because there's less insulation from cosmic radiation. So parts of the stratosphere are warmer than others. And they're based on temperature variations, how they describe them. The mesosphere is in between the stratosphere and the outermost one. The thermosphere is the one that gets hot. It's going to have exposure to the outer, well, it's not exposed to cosmic radiation and less shielding from the sun. So it's a thermosphere. The mesosphere then is between the two. Where in the world then do jets fly? In the troposphere. So yes, it's very cold, but no, they don't really go that high. Not 20 kilometers by any means. So we're in that kind of range. Things to remember or think about. So if we are talking about other aspects of the Earth's atmosphere, we need to think about carbon dioxide levels. And you've heard about this perhaps in the news. I hope you have, because it's been in the public conversation for quite a few years now. Scientists have determined that the concentration of atmospheric carbon dioxide has increased a lot in the last 160 years, from about 290 parts per million, in other words, that low level shown at the left on the graph, about 1850, to a current level of much higher than that, in 390 or beyond, and this graph only goes out to 2010. And the global atmospheric warming is likely to be occurring as a result. Where does these CO2 levels come from? Carbon dioxide is a gas, right? It comes from the increased use of fossil fuels in industrialized societies, as we have had equipment and machines and vehicles that are burning fossil fuels like coal and gasoline. It's combustion, and the product of combustion is CO2. So CO2 combustion has to do with, evolution has to do with all the fossil fuels being burned. And the warming of the troposphere in the last 25 years is certainly evident. The troposphere, the part where we live, where things grow, it's very evident. And potential warming by 2050, which isn't so far away all of a sudden, could cause some serious consequences in terms of melting glacial ice, ocean levels rising, and coastal cities on all various continents, especially in the US. You can think of a lot of cities that are in the coastal regions could be severely impacted by the rising ocean levels. Florida people have heard this conversation quite clearly. So here's another chart that gives us some information about temperature changes. This is from an ACS, American Chemical Society, Climate Science Toolkit. And this isn't going out quite as far as some other data might have. But there are computer models that predict a continual warming up to 3 degrees Celsius, increase more by 2050, which could contribute to glacial ice melting and ocean levels changing. So if you look at the mean temperature of land and ocean temperatures, the temperature anomaly is graphed on the left versus time, and there's a lot of interesting ways that scientists have come up with this data, which is not for this conversation. But if you look at the average back in 1890 as the green bar on the left side of the graph, was the average temperature change back there was between -2 and -4 from the current average. The average around 1945 is in the middle, which is up to 0 and above. And now the average temperature changes are up here, way up in up the positive range around 0.5, 0.6. So you can see over time, overall increases are evident. You can look at annual means with the black dots, or the 5-year running mean is a smoother graph with a red line. And the trends are conspicuous. They're continually increasing. The land-ocean temperature index shows definite increases. There are those who deny that this is anything other than just natural progressions, but scientists will argue otherwise, that the influences of humans in industrialization has certainly impacted the amount of carbon dioxide and how the temperatures have increased globally. Increases in carbon dioxide, again, are related to increased uses of fossil fuels, particularly coal, but not only that. And so looking at carbon dioxide, methane, and nitrous oxide, these are all greenhouse gases, and how they've all changed over time. Values in these figures for the past several decades are measurements of atmospheric composition of each of those gases. The graphs are labeled differently on the two sides. The methane's on the right with a different scale. And the earlier values are from ice core analyses, which is an interesting approach to getting things. So the ice core analyses have to be the ones they're going to use from much more distant time zones. And look at how they have all changed. So the levels from year 0 to 1500 fluctuate certainly, but there's no general trend. There's fluctuations and no particular trends. So once you get up to, say, 1800, they've been kind of steady for hundreds of years. But then after that, all of those levels have skyrocketed relative to where they were in previous centuries. So there's a clear indication of how much change there has been in recent decades compared to centuries ago. So is the Earth getting warmer? Well, this is interesting because I've taken data from the absolute, the Grand Forks newspaper even reports these things. And this was one that was reported at the beginning of 2015, which isn't exactly yesterday, but this is the most recent one I could find at the moment. So they're reporting temperature data, and 2014 was a warm year for a lot of folks' recollections. But how much warmer was it, and was it significantly warmer? So reading this data here, the average temperature was 1.24 degrees Fahrenheit above the 20th century average, which was another number, but let's just see how much it's changed. Nudging out these other rivaling years of 2005 and 2010 by a very small amount. And the briefing from NASA said that 2014 was the warmest in its database, but its method of calculation is a little bit different. The margin of error then by the National Climatic Data Center, that's what CDC is here, suggested that, whoops, I didn't want to take that, well, okay, I can't do it, that the temperature for the margin of error was 0.16, but they're 2.5 times more likely that it was warmer than those two previous years. So they have a little bit different margins of errors. So worldwide temperatures have changed ponderously from year to year, but never more than half a degree Fahrenheit. And they were 1.24 degrees Fahrenheit higher than the 20th century average in 2014. That sounds like more than twice the change. In other words, that's consistent with this 2.5 times more likely that it was warmer than other years, because that's a very much larger change than these other things had reported. There is evidence that the Earth's temperatures are increasing. So what else about the Earth's atmosphere? Well, the Earth's atmosphere has smog in it from time to time. This picture shows the horizon in a big city, and you can see this brownish haze that is the thing that makes people cringe, and you don't want to breathe the air if that's where you are. And it's photochemical smog, in part a result of pollution from automobile exhaust. The brownish color is contributed by nitrogen dioxide, and a consequence of that nitrogen dioxide, it is created in part from combustion of automobile fuels, and it comes in the exhaust because nitrogen is in the air, and nitrogen in combination with the oxygens gives us these various oxides. Well, photochemical smog is referring to the fact that light is going to react with the NO2 that's produced. And one of the results is that you get nitrogen monoxide formed, which is also not a particularly pleasant thing in the air. Doesn't necessarily have the same color. But then oxygen atoms, atomic oxygen results as a consequence of that photo reaction with light from the sun, making it possible for the oxygen atoms to combine with oxygen gas to make ozone. And we've all heard about ozone as being an issue. So ozone is part of our hazardous things at ground level because ozone is an oxidizer. And it causes various kinds of problems because of that. So what else is there to think about the Earth's atmosphere? And these are all related to gases. So these are related to the last 200 years of industrialized societies. We burn hydrocarbons, but they're not always completely combusted. When they get hot, some of them vaporize and end up in the air. And the production of nitrogen monoxide from combustion of petroleum products at industrial plants and in vehicles combines then further with oxygen making NO2. So all of these are problematic reactions from the burning of hydrocarbons and incomplete combustion both. And it gives you that ugly smog that we see in this picture. Another consideration about gases in the air has to do with burning of coal. Burning of high sulfur coals, which are what are characteristic in certain locales, gives us products like sulfur dioxide when it reacts with air. And the sulfur gets, in those high temperature burning situations, turns into sulfur dioxide, which when it is in sulfur dioxide combines with oxygen, now makes sulfur trioxide. And sulfur trioxide eventually then is potentially going to react with moisture in the air, liquid water, to make sulfuric acid. Oh, sulfuric acid in the air. That sounds really weird, but it's aqueous sulfuric acid that results. And what happens is it precipitates when it rains, literally from the air, and that's what acid rain is all about. Now, acid rain is a lesser consideration than it once was because high sulfur coal sources are less and less used. But what happened with this acid rain? Acid reacts with marble. And statues like shown in this picture here are clearly weathered by acid rain. These marble reacts with sulfuric acid to make carbon dioxide, calcium sulfate, and water. And so the more the exposure to acid rain or acidic rain conditions, the more these statues have deteriorated in various places over time. The result has been hazardous in other ways as well from acid rain. But it only occurs slowly in air with each of these steps to create the CO2. You go from the solid marble to make CO2. And those poor statues look like they've had it, don't they? What else is related to acid rain is the hydrogen ion concentration in the air as pH from measurements made at a laboratory in 1996 compared with one at a later time. So the pH is low when it's acid or more acidic. And so the worst areas are the reddish colors. The most intensely affected or most acidic compared to others are these regions in the northeast in the US. You can see there are conspicuous concentrations of lower, more acidic conditions in 1996. But thankfully, a comparison with the later data in 2009 shows that those are much, much, much reduced. So the use of high sulfur coals has been reduced enough that acid rain effects have diminished. And that's a good thing for trees too. The last part of our conversation then about gases has to do with what ozone does in the upper atmosphere. The ozone layer is 20 to 40 kilometers above the Earth's surface. Ozone, O3, is a pollutant at low altitudes, but it's critical in the upper atmosphere. You realize, you've heard this, I suspect, that it's important in the upper atmosphere because it absorbs UV radiation that otherwise causes things like cataracts and skin cancer. For all of us who are anxious to get outside and enjoy the sun, we are hoping that we don't get too much exposure to UV radiation, and ozone helps block some of that. So the lowest, we've seen these maps probably somewhere with false color satellite images of ozone, and this one was from, let's see, I just covered that, from 2009. The lowest ozone concentrations are represented by purple and violet regions, and you can see where some of those are over Antarctica. There's a little interesting in the contrast in this image here, a little difficult to see where the darkest regions are. And the purple and violet regions are some extra dark ones over Antarctica. Antarctica overall looks violet, I would suppose. And comparing this to another satellite image at another date, that was 2009, here's 2011, there's a lot of ozone depletion evident. So ozone levels are up to 50% lower than normal, and this is a significant cause for concern in our thinking. So ozone, where does that come from? What's that all about? Well, that's another gas question. Cause of ozone depletion, has to do with these funny things called chlorofluorocarbons that were used for a very long time in aerosols and refrigerants and as solvents for a lot of reasons. They're not toxic, they're not flammable. In fact, they're used in fire extinguishing products. And they are not corrosive, but they are not easily biodegradable. And so once released in the environment, they just persist. They diffuse to the stratosphere from ground level, and their worldwide use was banned in 1987, so it's been a while. But there was an international ban finally within 10 years there, but there has been reported millions of dollars of illegal per year of illegal chlorofluorocarbons still made in some countries that were not adhering to the international ban. Well, of course, 1996 is quite a while ago, but that has where the impact on the ozone layer was finally evident and was time to take action internationally. But where does it come from? It's the chlorofluorocarbons, such as shown at the left in these equations, reacting with light to make chlorine atoms. The chlorine atoms combine with ozone and turn it into oxygen and a chlorine monoxide, which is really curious, and that makes other things like dichloro dioxygen, which is pretty funky, or dioxide, and dichlorine dioxide. Whatever the case is, the net process ends up turning ozone into oxygen. Up in the upper atmosphere where it's exposed to light, the ozone is being broken down by light to oxygen. Now, oxygen's fine, but we need some of that ozone up there in protecting us from UV radiation and such. And ozone is noted over here on the right, was something was discussed when we talked about resonance structures. And so there's a lot of chlorine atoms that are generated, and they lead to destruction of ozone. So all of these things are things that are gas-related and impact our environment, and something we should be aware of as citizens. Okay, I hope you found some of this informative. Even if they make lousy test questions, they'll make you a better citizen if you have some awareness of these things. Good luck studying. There's tests coming soon. See you in class.